Hello, everyone. Today I will talk about the cryptanalysis of the stream cipher Draco. Um, so in Asia Crypt of 2001, Alex Pirukov and Adi Shamir published their seminal paper on TMG trade-off attacks. And the main conclusion of the paper was that for a stream cipher to be secure, the size of its internal state in bits needed to be at least 1.5 to 2 times the size of the secret key that it uses. This was generally accepted as the rule of thumb until the FSC of 2015, in which Amnek and Mikhailev proposed the stream cipher Sprout, whose internal state was exactly equal to the size of its secret key. Surprisingly, the cipher did not succumb to generic TMD trade-off attacks and was much smaller in area than any known stream cipher at that point because of the small state size. Now, a stream cipher is a finite state machine. If we consider f to be the function that maps the internal state of the stream cipher to a key stream vector of equal size, then the cryptanalysis of the stream cipher reduces to inverting this one-way function f at any one of the key stream segments that the attacker has access to. Now, the algorithm that Birukov and Shamir proposed had the trade-off curve mt squared times t squared equal to n squared, with the limitation that t had to be larger than d squared, where m, t, and d are the memory, online time, and the data complexity of the algorithm. Capital N was the cardinality of the internal state space, and the offline complexity was given as n divided by t. So the main idea is that in the offline stage, the attacker chooses some random initial states and iterates this one-way function f that maps the state to the key stream a total of t times and stores the endpoints in a table. In this way, the attacker covers a fraction of the set of states that the cipher has. And in the online state, the attacker states one of the key stream segments and tries to see if it is present in any one of the tables. A typical point on this trade-off curve is where both capital T and capital P are capital N to the power 2/3, which is less than n. If capital K denotes the cardinality of the key space and n equal to k, which is to say that the key and the state size are equal, then this trade-off point represents a valid attack against the stream cipher. So as a rule of thumb, capital N was set to k squared, after which it is not possible to find a point on this curve for which both capital P and capital T, the online and the offline complexity, are less than capital K. Okay. So the main idea behind Sprout and similar stream ciphers which have shorter internal state is that the state update function required the secret key as the input. And so any of these maps that maps the SIs to the ZIs, it is not possible to construct this function f that maps the state to key stream without the input of the secret key. So this made the effective state size of the cipher basically equal to the size of the state plus the size of the key, which was effectively twice the size of the key. And so any generic TMD trade-off type attacks could have been prevented, or were prevented. Of course, Sprout had other weaknesses, and it was attacked in a number of papers following its publication. And since then, there have been various attempts at designing short-state ciphers. For example, Plantlet was a redesign of Sprout by the same authors by removing known points of attack from the design. However, there was a near collision attack reported against it in the FSC of 2019. Lizard was another design presented in FSC of 2017. And there are some attacks reported against Lizard in the FSC of the following year. Atom was another design presented in FSC last year, and we're not aware of any attack report against it. So Draco was designed presented at FSC this year. Those familiar with the structure of the grain family of stream ciphers will recognize this setup immediately. So it has two nonlinear registers of size 95 and 33 bits. And the state is updated with a 128-bit non-volatile state, which consists of the first 32 bits of the key and the 96-bit IV. By XORing this bit D of t to the update function at every clock cycle. Now, D of t is constructed as follows. First, the IV is prepended with a single 0 bit to make it of 97 bits. And the bits are renamed as xi. And dt is then calculated as x of t mod 97, XORed with k of t mod 32. It was probably done because 32 and 97 are co-prime. And so it would be more difficult to construct patterns in the dt sequence. Now we have proposed two attacks on Sprout, and I will very quickly take you through both of them. The first attack stems from two observations. The first thing to note is that the sequence d of t is periodic with period equal to the product of 32 and 97. This is not very difficult to see since dt is just a XOR of the IV and the key bits, and since the IV and the key bits repeat in cycles of 32 and 97, it is therefore understandable that they will come into sync after 32 times 97 cycles. And so sequence dt will be periodic with this given period. The second observation is as follows. We take all IVs of the form kappa concatenated thrice and the whole thing rotated by 1 bit. But kappa is a 32-bit key prefix. For all such IVs, it is very easy to see that this 96-bit sequence d of tau plus 1 up to d of tau plus 96 is 0 for all values of tau that are divisible by this period 3104. Since dt is the contribution of the key to the update of the state, this essentially implies that the state update for 96 cycles, and in turn, the key stream bit generation for 99 cycles is effectively independent of the key. Well, the key stream is independent for 99 instead of 96 because in cycles 97, 98, and 99, the state bits are updated by the key. The state bits that are updated by the key do not take part in the construction of the key stream bit. And so there are relatively small numbers, so 2 to the power 32 IVs of the required form VVV rotated by 1. And so the strategy is using a chosen IV scenario and trying all possible IVs of this form and wait till V equals kappa. Yeah. That is when the cipher becomes weak algebraically. So the idea is as follows. In the offline stage, we try to create tables assuming that the stream cipher is already in this weak algebraically compromised state. So we generate random 128-bit states, generate the 99 key stream bits that does not require any involvement of the key. And then we store it in an offline table, indexed by the key stream vector, of course, so that it is easy to search. Now, in the online stage, we query key stream bits for all IVs of this required form. And we take, for all I that are 1 mod 3104, So we extract these 99-bit keystream windows and try to see if they are already present in this table or not. So if we find a match, we generate a few more keystream bits and check if the extracted keystream bits and the generated keystream bits match. If no, we can simply reject this candidate and move to the next keystream window. However, yes, then we can output the secret key. And by using birthday bounds, it's possible to calculate that the total complexity of this attack is around 2 to the power 114, as opposed to brute force search, which would take 2 to the power 128. The second attack stems from another key observation. So the idea is we take all initial vectors for which the first 96 minus capital E bits are 0. And the remaining capital E bits are some small vector, small e. Yeah. And now consider some lambda, which is a multiple of 97. It can be proven that the 97 minus capital E bit sequence, d of lambda to d of lambda plus 96 minus e, does not depend on this small e. And this is not very difficult to prove, and can be proven in 2 lines, as I've shown in the slide. But the main takeaway is that of the IV of this form, for any IV of this form, the state update for 97 minus e cycles, and for similar reasons, keystream bits for 100 minus e cycles do not depend on the IV at all. And this gives rise to another sort of weak configurations that we can exploit in the following way. In the offline stage, we try to create tables, again, assuming that the stream cipher is already in this weak compromised state. Only difference is that this time you have to construct tables for all the 2 to the power 32 key prefix values. So we take we generate 2 to the power 96 minus capital D random states, random 128-bit states, and generate this 100 minus E keystream bits, and store this pair keystream comma state in the respective table tab of K. The online stage is exactly similar. We take all IVs of the given form in which the first 96 minus capital E bits are 0. And then we take all 100 minus E bit keystream windows and see if they exist in any one of the 2 to the power 32 tables. And the rest is exactly similar as the previous attack. If you find the match, then you can output the key, then you can generate a few more keystream bits to check if the generated and the extracted keystream bits match, and output the key. Otherwise, move on to the next candidate. We can adjust the values of capital E and capital G to balance the offline and online complexities. And you've seen that for capital G is 28 and capital E is 40. The 2 complexities become the same, and the total complexity becomes around 2 to the power 107. And this is probably the best we can do in this setup. To conclude, it is obvious that the main point of entry of the attack was the schedule function and how the authors chose to construct the sequence D of T, which allowed us to define a very simple one-way function from the state to the key stream over a smaller over a set of smaller cardinality. My initial intuition is that a better key schedule should fix this design. And that is all I have in this presentation. Thanks a lot for listening. Thank you.